We are asked to diagonalize the following 2 by 2 matrix. An n by n matrix A is diagonalizable when there exists an invertible matrix P and diagonal matrix D such that matrix A is equal to matrix P times matrix D times the inverse of matrix P. To diagonalize a square matrix, number 1, we determine the eigenvalues of the matrix, which in our case will be lambda sub 1 and lambda sub 2. We use these eigenvalues to construct the diagonal matrix, where we have the eigenvalues along the main diagonal and the other entries are 0. The next step is to determine n linearly independent eigenvectors, which in our case will be vector p sub 1 and vector p sub 2. And then we construct matrix P by using the eigenvectors as the columns. And the last step is to determine the inverse of matrix P. So to begin, we need to determine the eigenvalues of the given 2 by 2 matrix by solving the equation, the determinant of the difference of matrix A and the product of lambda in the identity matrix equals 0. So I've already set this up below. We have the determinant of the difference of matrix A and lambda times the identity matrix equals 0. Simplifying inside the parentheses, we have the matrix where the first entry is 6 minus lambda, the second entry is 10, in row 2 we have negative 2, and then negative 3 minus lambda. Now we find the determinant, set it equal to 0, and solve. The determinant is equal to the product of 6 minus lambda and negative 3 minus lambda minus the product of 10 and negative 2. And now we multiply out the left side and simplify. Multiplying the two binomials, we have negative 18 minus 6 lambda plus 3 lambda plus lambda squared, which gives us negative 18 minus 3 lambda plus lambda squared, and then we have plus 20 equals 0. Combining like terms and writing the terms in descending order, we have lambda squared minus 3 lambda plus 2 equals 0. And now we solve the characteristic equation. In this case, it is factorable. The two factors are lambda minus 1 and lambda minus 2. Because our product must equal 0, we have lambda sub 1 equals 1 and lambda sub 2 equals 2. And now we use these eigenvalues to form the diagonal matrix D, where we have 1 and 2 along the main diagonal. The other entries are 0. The next step is to find the corresponding eigenvectors, which we will use as the columns of matrix P. So beginning with lambda sub 1 equals 1, to find the corresponding eigenvectors, we solve the equation, the difference of matrix A and the product of lambda and the identity matrix times vector x equals 0, where vector x is an eigenvector. So again, I've already set this up below. We have matrix A, we have 1 for lambda, and then we have the 2 by 2 identity matrix. Let's write the corresponding matrix equation. Let's check this coefficient matrix. The first entry is 6 minus 1 times 1, which is 5. Next in row 1 we have 10 minus 1 times 0, which is 10. In the second row we have negative 2 minus 1 times 0, which is negative 2. The last entry is negative 3 minus 1 times 1, which is negative 4. I've also written vector x as the vector x1, x2, and the 0 vector as the vector 0, 0. Next we write the corresponding augmented matrix and write the augmented matrix in reduced row echelon form. Notice there's no pivot in column 2, which indicates P2 is a free variable. The first row indicates x1 plus 2x2 equals 0, and because x2 is a free variable, we have x2 equals x2. Next, we will solve the first equation for x1 and then parameterize the solution by letting x2 equal t, which gives us x1 equals negative 2t and x2 equals t. This indicates that all the eigenvectors corresponding to lambda sub 1 equals 1 are in the form of the vector negative 2tt, or t times the vector negative 2, 1. This indicates all the eigenvectors corresponding to lambda equals 1 are all the scalar multiples of the vector negative 2, 1, except the 0 vector, because remember, an eigenvector can't be the 0 vector. So we can select any vector as the eigenvector corresponding to lambda sub 1. Let's just let t equal 1 and use the vector negative 2, 1, which will be the first column of matrix P. And now for the second column, we need to determine an eigenvector corresponding to lambda sub 2 equals 2. So we go through the same process again. Let's check the coefficient matrix. The first entry is 6 minus 2 times 1, or 4. And then we have 10 minus 2 times 0, which is 10. In the second row, we have negative 2 minus 2 times 0, which is negative 2. And finally, we have negative 3 minus 2 times 1, which is negative 5. Again, we have the augmented matrix, as well as the augmented matrix in reduced row echelon form. The first row indicates x1 plus 5 halves x2 equals 0. Again, x2 is a free variable, and therefore x2 equals x2. And let's again parameterize the solution by letting x2 equal s, which gives us x1 equals negative 5 halves s, x2 equals s. All the eigenvectors corresponding to lambda sub 2 equals 2 are scalar multiples of the vector negative 5 halves 1, again excluding the 0 vector. To avoid fractions for the second eigenvector, let's let s equal 2 and use the eigenvector of negative 5, 2 for the second column of matrix P. So now that we have matrix D and matrix P, the last step is to determine the inverse of matrix P. So there's a couple of ways to find the inverse of matrix P. I'm going to go ahead and use the formula shown above. Substituting negative 2 for A, negative 5 for B, 1 for C, and 2 for D, we have the inverse of matrix P is equal to the 2 by 2 matrix 2, 5, negative 1, negative 2. And now we have all the pieces we need for the diagonalization of the given 2 by 2 matrix. The matrix 6, 10, negative 2, negative 3 is equal to, again, matrix P times matrix D times the inverse of matrix P. These three 2 by 2 matrices form the diagonalization of the given matrix. And of course, if we wanted to, we could check this product to make sure we do get the given matrix. So you may want to take the time and do that. I hope you found this helpful.